In this presentation, we're going to talk about what are called imaginary numbers or complex numbers. Now, in your high school math classes, you were probably told many times that you can't take the square root of a negative number. When you're trying to solve certain kinds of equations, that's a problem. It means that, for example, some quadratic equations have solutions where others don't. Imaginary numbers or complex numbers are the solution to that problem. They're going to let us come up with solutions to any polynomial equation. Now, we're going to use the letter I to represent our new imaginary number. And you'll often hear people say that the imaginary number I is equal to the square root of -1. Now, it's sometimes convenient to think of it that way, but the technical definition is the one I have on the slide here. I is the number whose square is -1. Now, you might be thinking that if we take the square root of both sides of that equation, we get I is equal to the square root of -1. So insisting that our definition is I squared equals -1 instead may seem like we're being excessively picky, but as we'll see in later slides, it's going to be important to know specifically what I squared equals. Now, before we go any further, I want to go over some basic definitions. What I have here on this slide is what's called the standard form of a complex number. It has a real part and an imaginary part. For example, the number 4 minus 2i is in the standard form. Its real part is 4, and its imaginary part is -2i. Now, when we refer to the conjugate of a complex number, we mean the number with the same real part and the opposite imaginary part. For example, the conjugate of 4 minus 2i would be 4 plus 2i. Okay, if we want these numbers to be the solutions to equations, then we need to be able to do all of the things with complex numbers that we can do with real numbers. For example, we need to be able to do arithmetic with them. Adding and subtracting is done just like adding and subtracting with polynomials. You can treat the I just like you would a variable. In this first example, I'll combine the two real parts and then I'll combine the two imaginary parts the same way I would if I was trying to do something like simplifying 2x minus x. Subtraction also works the same way. I'll start by distributing the minus into the parentheses. Then I'll add the real parts together and the imaginary parts together. Multiplication also works the same way that it did with polynomials. For this first expression, I'll use the distributive property to distribute the 3 into the parentheses. That makes the expression 3 times 2 minus 3 times I, or just 6 minus 3i. For the middle expression, I'll multiply it out using the FOIL method. That's going to give me 3 times 4 minus I times 4 plus 3 times 2i minus I times 2i. Now, if I work out the multiplications, the expression becomes 12 minus 4i plus 6i minus 2i squared. I can combine the two imaginary terms to plus 2i, and that leaves me with this 2i squared part. This is where my being so picky with the definition is going to be useful. Remember that the definition says that I squared is equal to -1. So now I can finish the simplification by combining the 12 and the 2 to get 14 plus 2i. Now for the third expression, I want you to start by noticing that the two imaginary parts are conjugates of each other. Their real parts are the same, and their imaginary parts have opposite signs. So watch what happens when I do the arithmetic. This becomes 3 times 3, or 9, minus 3i plus 3i minus I squared. The 3i and the minus 3i cancel each other, and the I squared, just like it did in the previous problem, becomes -1. So if I combine the 9 and the plus 1, the expression simplifies to just 10. And this is always going to be what happens when we multiply a complex number by its conjugate. The end result is going to be just a real number. That is a number with no imaginary part. And that's going to be useful on the next slide when we talk about division. Okay, so this brings us to the last of our arithmetic operations, which is division. When we talk about dividing complex numbers, what we mean is we want to take this fraction, this ratio of two complex numbers, and simplify it to a single complex number in the standard form. In other words, I want to get the imaginary part out of the denominator. To do that, we can use multiplying by a conjugate because, as we saw in the last slide, when we multiply a complex number by its conjugate, the imaginary part goes away. So to simplify the first expression, I'm going to multiply the top and bottom by 4 plus I. That is, by the conjugate of 4 minus I. Now when I distribute the 2 into the parentheses, the denominator becomes 8 plus 2i. And when I multiply out the denominator, it becomes 16 plus 4i minus 4i minus I squared. Now the two complex parts cancel each other, and the I squared becomes -1. So the denominator simplifies to 16 plus 1, or just 17, which makes the whole expression 8/17 plus 2/17 I. Notice how I split the fraction up into two parts. This is customary with complex numbers because we want to have a clear real part and a clear imaginary part. Now, the second expression is a little trickier because there's a complex number in the numerator, but the process is going to be exactly the same. I'll start by multiplying the top and bottom by the conjugate of 5 plus I. and I'll multiply out both the numerator and the denominator using the FOIL method. That makes the numerator 15 minus 10i minus 9i plus 6i squared. And the denominator is 25 minus 15i plus 15i minus 9i squared. Now, I'll cancel the 15i's in the denominator and combine the two imaginary parts in the numerator. Next, I'll replace the I squareds with minus 1. And then combine the real parts. This is 15 minus 6, which is 9, and 25 plus 9, which is 34. And finally, I'll split the expression into a real part and an imaginary part to get the final result. Now, the last arithmetic type thing we need to be able to do is simplify powers of I. And the first two are easy. I to the first power equals I, just like it does with numbers and variables. And I squared is equal to negative 1 based on our definition. Now, to simplify I cubed, I'm going to think of it as I squared times I. Because I squared is equal to negative 1, this simplifies to just minus I. Similarly, I'm going to write I to the fourth as I squared times I squared, which is minus 1 times minus 1, or just positive 1. Okay, that's where things get interesting. Take a look at I to the fifth. If I rewrite this as I to the fourth times I to the first, the I to the fourth part becomes 1, so this is just I. Similarly, I to the sixth is I to the fourth times I squared, or 1 times negative 1, which is just negative 1. I to the seventh is I to the fourth times I cubed, or 1 times negative I, which is just negative I. And finally, I to the eighth is equal to I to the fourth times I to the fourth, which is 1 times 1, or just 1. Now, compare the numbers in these two columns and notice how they repeat. This repetition is going to continue for higher powers, like I to the 9th, 10th, 11th, and 12th, and that's going to give us an easy way to simplify large powers of I. Okay, take a look at I to the 48th, for example. 48 is equal to 4 times 12. So I can rewrite this as I to the fourth to the 12th power. But I to the fourth is just 1, and 1 to the 12th is also 1. So I to the 48th must equal 1. Now, I to the 117th is a little different because 4 doesn't go into it evenly. So here's what I'm going to do. If I rewrite 117 as 4 times 29 plus 1, I can rewrite the expression as I to the 4 times 29 times I to the 1st. I to the 4th is just 1. So this is equal to I. Now, rewriting 117 as 4 times 29 plus 1 may have seemed a little complicated. So here's a simpler way to come up with the result. If you take 117 and divide it by 4, you get 29 with a remainder of 1. And it's the remainder that gives you the end result. The expression is going to simplify to I to whatever your remainder was. In this case, that was 1. So I to the 117th simplifies to I to the 1st, or just 1. Okay, now take a look at this last expression. If you divide 82 by 4, you get 20 with a remainder of 2. Now that tells me that I to the 82nd power is equal to I to the 2nd, or just -1. Now we finally come to the solving equations part that I talked about as being the goal of coming up with these complex numbers. This first equation we can solve using the square root principle. I'll start by subtracting 9 from both sides. And then I'll take the square root of both sides. The right side becomes plus or minus the square root of -9. Now you can think of this as the square root of -1 times 9. The square root of -1 is I, and the square root of 9 is 3. So that makes the final solution x equals plus or minus 3i. Now with the second equation here, we're going to have to fall back on the quadratic formula. And looking at the coefficients, we have a equals 1, b equals 1, and c equals 2. So if I substitute those into the formula, I get x equals -1 plus or minus the square root of 1 squared minus 4 times 1 times 2 divided by 2 times 1. The expression under the square root simplifies to 1 minus 8, or just -7. And now I'll use the same reasoning that I did on the first equation. -7 becomes -1 times 7, and the square root of -1 becomes I. And the square root of 7 can't be simplified any further. So that makes the final solution x equals -1 plus or minus I times the square root of 7 divided by 2.